Okay, well, we get started here. So today we will we'll finish up factor analysis, perhaps get to a little bit of cluster analysis, and we'll also do a test number 2 review. Are there any questions before we begin? Okay, so again, we're talking about this factor analysis model where we have our, let's say, our original variables standardized. We set them equal to a linear combination of some f's, which is our common factors, lambdas, which is our factor loadings. Our goal is to try to estimate these factor loadings. These are parameters. And because these f's and lambdas might not perfectly describe the corresponding z's, we have an additional set of terms at the end called the specific factors. Okay. Now, actually, let me come back up here. Now, you remember from principal component analysis, we found principal component scores, which were the values of these, or the actual numerical values of these new variables that we were forming. But we would like to be able to do something very similar to that now with the f's. Find their actual numerical value. So for observation 1, there is an actual numerical value for f1, for f2, and so on. For observation 2, there's a value of f1, there's a value of f2. We like to be able to calculate those. Maybe do some plots, very similar to when we work with principal component scores. So that's the main thing that we're going to be doing here today. But first, there's one little thing I need to talk about regarding these rotation methods that we were discussing before. So if you remember, we can come up with essentially different values of lambda by applying an orthogonal matrix to the factor loadings in terms of multiplying them. And that can give us then a new interpretation of the f's, which hopefully are easier to interpret now with these new lambdas. So really briefly to review, here's where the original, what these original lambdas were for the goblet data, where each of the W4, W2, and so on represents a pair of these lambda hats. We have two common factors. And when we do one of these factor loadings and find one of these orthogonal matrices, what we're hoping is that we can now find a set of factor loadings that are primarily equal to -1, 0, or 1, because that will help us interpret our new variables that we're forming, these common factors. And so what we said is, well, maybe what we could do is actually rotate the axes like this, set up a new set of axes, and now this might be a little bit easier to interpret. In this particular case, it was a little bit easier because notice where W1 and W2 are located, as also W6. In those three different cases, we're going to have some factor loadings that are close to 0. Okay? But let's say we have a situation like this. This is not what we have, but let's just say we have something like this, where we have, let's say, some factor loadings that appear right about here. We have some factor loadings that appear right here as well. And so, you might be wondering, well, could we, when we do this rotation, rather than always keeping this, let's say, perpendicular, or larger sense, orthogonal, maybe we could rotate these axes so that it looks something like this. Okay? And in this particular case, that will be quite useful because those corresponding factor loadings are going to be typically, some of them are going to be 0, some of them are going to be close to +1. And so when one does that, that's what's called an oblique rotational method. But the problem is that now these new axes that we have are no longer perpendicular to one another, or orthogonal, which means then that these axes are essentially representing our common factors. And our common factors now are no longer then independent. So you can think of, and we've talked about this before, how you can think of orthogonality being kind of equivalent to independence. And so now the common factors are no longer independent of one another, which violates some of the underlying assumptions that we have with our model. So for that reason, I've never actually applied these methods. But I just at least wanted to tell you that they do exist, and some people do use them. So this information is what actually is located on page about 40 and 41 of the notes. Okay. Now we're going to come back to this common factor scores. There are two different calculation methods for these common factor scores. Both of them rely on students having taken, let's say, a regression analysis course, such as Stat 8-7. And I know most of you have not. So what I will do here is try to explain it the best that I can in terms of give you some intuitive feeling for it. If you want to understand this further, my Stat 870 notes for our regression analysis course, or course online, Chapter 11 of my notes contain a good explanation of it, and also, either Chapter 3 or Chapter 4 of my notes. Okay. So our goal here is to actually come up with numerical values for F for every single observation. That's our goal. And the first method that we're going to be talking about is something called Bartlett's method, which is also known as weighted least squares method. Now, all of you know what a least squares method is relative to regression analysis. What you might not know, since if you haven't taken like a Stat 870 course, there's extensions of weighted least squares to the following case. So this is a typical model representation of a regression model where I have just one particular variable. One explanatory variable x. So I put an I there to emphasize this is for, let's say, the ith observation value. Y is the response. The key is that these epsilons are our error terms. Notice how they have those specific factors are kind of the same thing. These these error terms are random variables. They're assumed to be independent. They're assumed to have a normal distribution with a mean of 0 and a variance of sigma squared. This is for every single observation, sigma squared. So they have the same variance. Now, unfortunately, there are situations where that same variance assumption is violated. And what can one do? Well, instead of estimating your model using the least squares method, we estimate our model using the weighted least squares method. This is what's discussed in Chapter 11 of my Stat 870 notes. And so it's a very similar way of doing estimation. The only difference is that now we take into account that each of those variances could be different. And essentially those variances end up helping us become like a weight during the weighted least squares estimation process. A formal representation then of what happens is this. So if I write now my model in terms of matrices and vectors, notice the epsilon there has a normal distribution with a mean vector of 0 and a covariance matrix of sigma. If you want to, you could assume the covariance matrix diagonal, where each of the diagonal elements could potentially be different. And so normally with regular old least squares, and we saw this earlier in the course, in terms of matrices, we would think our beta hats are estimated by x prime x inverse x prime y. With weighted least squares, we now have to insert estimated covariance matrix. That's the only difference. Okay? Now, with that as background, hopefully gives you some idea, some intuitive idea of where we're going to go with this. Here's our factor analysis model. Notice how that model kind of looks like a regression model. And so for every single observation, let's say we're just going to take a look at, let's say, the rth observation to be general. Our goal will be to find f. So f contains f1, f2, f3, all the way down to fm. Our goal is to basically find an f that minimizes this expression here. So you take for your rth variable, take the standardized numerical values that you have, put them in a vector. Subtract off your lambda hat matrix. Doesn't matter if you're working with the Varimax rotation method or not. Here's my f that I'm trying to find. Then I have a psi hat inverse here. Does anyone remember what the psi hat matrix, or the psi matrix is?
It's environments for the unique.
Yeah, it gives the uniqueness, it gives the variances of the specific factors. So it's a diagonal matrix. So we take the inverse of it. And then over here, we have the z sub r minus lambda hat times f as well. So for the rth observation, we're going to try to find the f that minimizes this expression. Now, if I go back to regular old least squares estimation, essentially what we're doing there is this. We are trying to minimize this expression there. Notice how that looks very similar to what we have here, but you don't have that matrix that's in the middle. Now with weighted least squares estimation, we end up putting this in the middle. And we end up trying to find the value beta that minimizes this expression. And so hopefully you can see then now some relationship between weighted least squares to what I want to do here to try to find the f that minimizes this expression. And again, to try to put this into some kind of intuitive sense, notice this z minus lambda hat f is sort of like a residual. Okay? Think about, again, what we do with least squares estimation. We essentially have like a residual there. We are minimizing the sum of the squared errors. If you remember that from your, when you've done, regression in a steady to one like course. So, it can be shown then that the f that actually minimizes this has a closed form in terms of I can actually write it out. I don't need to do iterative methods. And it ends up being this expression here. Compare that these two equations. Eventually I'll get there so I can highlight. They're essentially the same equations, just now for a different kind of model. And so what we need to do is actually calculate this, we're going to call f hat, since this is now an estimated value. We need to calculate this f hat for every single observation. Those are going to contain our common factor scores for every single observation. Any questions about that? Okay. So that's method number one. Method number two is Thompson's method, also known as the regression method. Now, if you've had a full formal regression class, you know that there are two ways to think about your regression model in terms of the x's. You can think of these as fixed constants, and that's the way that it's usually taught. These are just constant values. The random variable is y, the random variable is epsilon. And you can use the least squares method then to come up with the parameter estimates for the betas. But in a full semester-long regression class, you learn about a different way to think about this regression model. And that is the x's are also random variables as well. In the end, you still get the same estimates for your betas, whether you think of the x's as constants or if they're random variables. So that's why, at least in a Stat 801 course, it's not even mentioned. But in a Stat 870 course, it's mentioned a little bit, and then you move on because you get the same thing in the end. So when we think of this now in terms of random variables, what we could do is, let's say, put all of our y's and all of our x's, let's say, just to make things easier, let's say we just have one explanatory variable. We could put these into a vector. And this would have a multivariate normal distribution with some kind of covariance matrix. And then what we would say is, okay, if I know what the x's are, after all, I am going to observe them, let's find the expected value of y given x. And then proceed within that kind of a framework for your regression analysis. So in the context then of what we're doing here, let's put all the z's and all the corresponding f's into a vector. So this part here is m by 1. This part here is p by 1. So in other words, we have a vector now that is p times m by 1. This, if we make the multivariate normal distribution assumption for everything now, like what we do for maximum likelihood estimation, this has a multivariate normal distribution with a mean vector of 0. Remember how the f's, we assume they had a mean of 0. And of course, when we have standardized variables, they have a mean of 0 as well. Remember also, the covariance matrix for standardized variables is equivalent to the correlation matrix. Also remember, and we actually even talked about this a little bit earlier, remember how the f's are assumed to be independent of one another with a variance of 1. And so what we could do to form the covariance matrix now for the ZF vector is basically form what's often referred to as a block matrix, where the first block, the 1, 1 part of the block represents the covariance matrix for Z. The 2, 2 part of this block corresponds to the covariance matrix for F. And we also know from past stuff that we've done, the correlation, let's say, between Z1 and F1 is lambda 1, 1. So if we put this more of a matrix context, then the covariance of the Z vector, the F vector, is the lambda matrix. So this is what it looks like. Then given that then, you might be wondering, okay, if I know what the Z is, and suppose just so that we can differentiate it, suppose we call the known Z value Z star. This would be like, let's say, the first observation, all the Z's, or the second observation, all the Z's. I'm just trying to be general here. Then you might say, okay, if I know the Z's, then what would I expect on average F to be? So what I have here is what's called a conditional expectation. Given something, what would I expect on average my random variable to be? You've seen conditional probabilities before in a Stat 801 like course. It's the same concept here. And one can show in this particular setting that expected value ends up being lambda prime P inverse times Z star. Again, if you were to take a Stat 870 course, you would see a direct relationship with that kind of a model representation. And remember what we're interested in, the big picture here is we want to know what are numerical values for those common factor scores. So how about we replace the unknown parameter values, the lambdas, with their estimates. So notice now I have a hat here. Also, this z star is going to be, let's say, for the rth observation, one of my z's. And then this p matrix here, how about we replace it with its estimate that comes about through our factor analysis model. And then you can say, voila, now I have a way to estimate my common factor score for a particular observation. Common factor scores for a particular observation. Okay. So that's the second method. Now, fortunately for us, we see that we have these messy equations here. Fortunately for us, we can use the fact_anal function R and then include the scores argument to do the calculation for us, where we can specify, do I want to do Bartlett? Do I want to do regression? Now, in terms of what you are responsible for with respect to what I've been talking about on pages, I guess, 43 and 44 here. I guess also 42. You're responsible to be able to understand how to do fact_anal to get the scores, but also understand this matrix representation such that you could actually program in this matrix representation into R and find the factor scores as well. I will have examples of how to do that. In terms of the relationship between these common factor scores and what is weighted least squares and so on, you're not responsible for that. But you are responsible for being able to program in the matrices here and also to use the scores argument in fact_anal. Okay, so let's now take a look at an example. So we're going to go back to the goblet data. Everything's the same in how I've used the fact_anal function, except for now let's say I say scores equal regression. And what's going to happen is that R is going to put the corresponding scores for every single observation in the scores component of the list that is actually returned to us from using the fact_anal function. So for example, for the very first observation, the first common factor score is negative 0.1349, negative 0.139. So this is the estimate of F1 for the first observation. The estimate of F2 for the second observation, the estimate of F2 for the first observation is negative 0.895. Now, how are all these calculations done? Oops, I didn't want to do that. Excuse me. So just to show you that indeed you could do all the calculations yourself, I actually programmed in the corresponding matrices. So just to review, notice I have the word solve here because I'm going to find the inverse. Then I have a lambda hat, and it's going to be transposed. So notice I take the transpose of that loading matrix. I multiply it by the inverse of sigma hat inverse, which equivalently would be take all those specific factor estimated variances. Remember, they're stored in the uniqueness component of our returned object. Since I have a diagonal matrix here, I use the diag function. And also, since I'm doing the inverse, I just simply take 1 divided by all those uniqueness values. Then I multiply again by lambda hat. Then I have again a lambda hat that's transposed. There's my inverse of that psi hat matrix. And then if I have, let's say, all the standardized values stored in a matrix called Z, I take the first observation or first row, and I get my Z sub R or Z sub 1 from that. And here are my common factor scores.
You're looking at the Bartlett.
Okay, I'm sorry. Well, I messed up that description. Instead, here's the corresponding code that just programs in the matrices, and I do get exactly the same. So, make sure you can run the code, and you can apply it to a new data set if needed. So for the Bartlett method, I say scores Bartlett. Here are my common factor scores. Notice the values here, negative 0.114, negative 0.914. Notice how they're a little bit different. You shouldn't expect it to be too different. They won't be exactly the same, generally, but there's going to be small differences. So let's do a plot of the common factor scores. So I can use the same kind of code that I use for the principal component scores. So I'm not going to go through the details of that. I'm also going to plot then the corresponding observation number for a common factor score by using the text function. So here's a plot now of the common factor scores. And I just decided to do the regression method. And what we can see here is that it's kind of similar to what we saw previously with the principal component scores in terms of where the observations are located, in terms of which are located near each other. So for example, here's 17, 4, and 5. And then with the principal component, notice how 17, 4, and 5 were all kind of next to each other, far from the other main observations. Take a look at 24, take a look at 23. Compare that to what we have with principal component scores. We get something similar as well. One thing that's a little bit different is notice how 2 is kind of separated from the main clump of points, where previously 2 was right here. Okay? But notice that 2 was a little bit different, at least in terms of the third principal component, because notice how small that circle is compared to all the large circles that were around it. And so perhaps, even though we're only using 2 common factors here, perhaps that's what we're seeing with that. So once again, what you could do with this plot is that you could identify outliers. So for example, 24 looks to be like an outlier. You can identify trends that we see. You can identify potential groupings of observations. So for example, if I were to just kind of do an ad hoc grouping here, I might do this and combine those two together. So that will be my grouping. And it's somewhat similar to what we have seen with principal component analysis, which somewhat makes sense because the goals, the overall goals are very, very similar. So here's a question for you. Suppose I use a different rotation method. Could the plot change? Yeah. Because now my common factors are representing different bits of information. So the plot could change. Okay. So that concludes in the factor analysis section. Given the time here, I want to make sure that we have enough time to go through the test review. So we'll jump to the test review now. And if there's still a little bit of time remaining at the class, maybe we'll go to the cluster analysis section. We'll start that as well. Okay, so let's talk about test number 2. Test number 2 focuses on graphics, principal component analysis, and factor analysis. Since we just got done doing the factor analysis scores, I'll make your life a little bit simpler, and I will tell you that's not on the test. Okay? It could be on the final, but it's not on this test. The actual test format is essentially the same as our previous test, but still I think it's helpful to go through some of the elements here just to make sure there's no confusion about what's going on. Last week, even though I didn't announce it, I put a formulas and functions PDF on my course website, on the graded web page. You can use that sheet to, let's say, quickly find stuff as needed. This is a closed book, closed note, closed video test, so don't use my notes. Do not talk to other students in the class when you're taking the test, but you can use any of my R programs on my website, functions, formulas, PDF. You can use the R help as well. These computers still are not set up for the RGL package, so you will not need to actually implement the RGL package, but I could ask you questions like, here's a 3D scatter plot of the principal component scores. Interpret it. We will start the tests at 8 a.m., at least I will make it available. It's going to be in a Word file. Put all your answers in this Word file. At times you might need to type out equations, and if so, you're welcome to use the text-based equivalent of that corresponding equation. Please email to me the test by 9:45 a.m. Do not leave the room here until you receive a confirmation from me that I've actually received the test. Obviously, computer problems can happen. Bring a laptop if you want to be extra safe. Obviously, we do have extra computers here, but it still can be helpful to have a laptop with you just in case. The number one issue that sometimes that students have with my tests in this kind of a format is the speed in completing problems. If I ask you on the test, well, state the factor analysis model for this data set. That's a common question I often ask. If it takes you 20 minutes to figure out the corresponding code to get the factor analysis model information out of R, and then obviously you need to type out the model, that tells me you haven't studied enough. So if you're taking if you're taking 5 minutes, 10 minutes, trying to look through the code to try to figure out how to do stuff, you haven't prepared enough. And that's where students sometimes falter with taking these kinds of tests. Even though there is some, open access or open aspect to this test, you do definitely need to study. And you need to think about it in terms of speed as well, because you have an hour and 45-minute time limit. Okay, any questions about the format? Structure of the test. Remember, always show your work. So any R stuff that you do, for example, I need to actually see the corresponding code. Because very frequently, I will actually try to execute your code to figure out, okay, what went wrong in your actual numerical value that you're presenting. If you don't give me that code, I don't have a way to try to figure it out. And then I don't have a way to give you partial credit. So showing your work is to your benefit. It allows me to assign partial credit if possible. The problem types will be, typically, I have a data set here. I want you to do some data analysis with it. I want you to interpret it. So you're going to need to use R for some problems. Other problems you might need to interpret it. Or other problems you might need to, let's say, show me you understand what's going on in the background in terms of what R is actually doing. Then there's going to be one set of short answer questions at the end of the exam as well, where each problem is not necessarily connected to one another. Now, in terms of the material that we've talked about, we obviously started off with the graphics section. Understand how to implement all the different plots that we looked at. What's the big picture of why we're looking at these plotting methods? Well, we're trying to get as many variables as possible being displayed on a plot. We want to understand the relationships between these variables. So we want to try to interpret what we see in these plots. So there was a wide, or I shouldn't say wide, but there was a number of different plots. We started off with simply a side-by-side scatter plot. Then we went to just a plain old two-dimensional scatter plot where we tried to, let's say, use the plotting characters to represent qualitative variables, categorical variables, where maybe we use the color of the plotting point to represent something. We talked about bubble plots. So now the plotting point corresponds to the size of a third variable. Make sure you know how to interpret them. If I say, for example, here's a bubble plot. Interpret the relationship between the three variables that are represented here. So in this particular case, you would say, okay, obviously if I have, let's say, x1 here, x2 here, it's simple to say, oh yeah, it looks like kind of a linear trend between x1 and x2. A positive dependence between x1 and x2. But if x3 represents the size of the circle, we see the same kind of positive dependence in between x3 with x1 and x2 as well. We can look at stuff in terms of a 3D scatter plot. And really probably the new, completely new kinds of plots that probably for you coming into this course were the star plot, parallel coordinates plots, and trellis plot. Since those are typically pretty new to students, I often like to give short answer questions about, describe to me what a star's plot is and how it represents multiple variables at the same time. So this will require you to write a few sentences out for this description. Like with the stars plot, you could say, okay, well, each variable is represented by a ray. And you could talk about how far the rays go out corresponds to the size of the corresponding variable. You could talk about, well, what does the middle of that star represent as well? Put this into words. But don't give me, let's say, a diagram. I want you to show me that you understand what it actually means in words, what this plot is doing, and how it represents multiple variables. Similar thing to be said about a parallel coordinates plot too, and a trellis plot. What is a shingle on a trellis plot? How are multiple dimensions or multiple variables, how do we get these extra variables on a trellis plot? So then we got into principal component analysis. That's when we started doing much more, let's say, mathier stuff in this course. Again, what's the overall purpose of principal component analysis? There's typically two things I always said about that. How does it work? Well, that's where eigenvalues and eigenvectors come into play. Can you write out principal component number one? Maybe I ask you to run print comp, but tell me what principal component number one is. Actually write it out formally yourself. You got to be careful in terms of how you write it out. Are we talking about the original variables? Are we talking about the standardized variables? Could you actually show me how you found, let's say, the score for the first observation for principal component number one? Not just necessarily use, let's say, the predict function R, but actually write out the actual formula that's used. Interpreting these principal components then is very closely related to these eigenvectors. I'll make sure if I say, okay, find two principal components. Now interpret them. With principal component analysis, we can use what's often referred to as either the covariance matrix or correlation matrix. Make sure you understand when one is preferred over the other. How do you choose the number of principal components? We talked about at least 3 different ways to choose principal components. There was lots of plots. with these principal component scores that we would look at. Think about, again, what we're after. Well, we just talked about it with respect to the factor analysis scores. We're after the same things. And make sure you're very familiar with using PrintCom. A good thing coming into the test would be to be able to actually type out PrintCom code without necessarily always having to look at one of my examples. That just helps you with the speed. If absolutely needed, you could go back to one of my programs, copy and paste some PrintCom code into your program and modify it. But I don't want you to have to memorize code, but hopefully now you've had some experience with it. You know the basic, well, here's the formula argument. This is what I need to put there. Factor analysis, what is its purpose? Well, it's very similar to principal component analysis. The key, though, is it's doing some stuff different. So what I could ask you as a short answer question is, what's the difference from, I could say something like this. Principal component analysis and factor analysis have the same overall purposes, but they achieve it in a different way. What's the main difference of what they are doing in terms of how they try to achieve it? And when it comes down to it, I don't want to fully give away the answer, comes down to, okay, principal component looks at the total variance. Factor analysis looks at the entire covariance matrix or correlation matrix. Now, with factor analysis, there was lots of terms. What I would hope would be an easy question is, let's say, on a short answer question, I would say, okay, here's a factor analysis model. For each of the components of this model, write out the formal name of what it is. So, you see an F. That's a common factor. Why do we typically use standardized variables with these factor analysis models? We have these factor analysis equations that we use. This is how, essentially, it plays a very important role here because it helps us see, for example, how there are times where we cannot actually use a factor analysis model because maybe we have, let's say, too many common factors, or we have, let's say, multiple solutions possible. This also plays a role then once we do the maximum likelihood estimation. Because now that covariance matrix, or again, if we're working with standardized variables, equivalent is the correlation matrix. We have a way to get the model inside that multivariate normal when we do the maximum likelihood estimation. Interpreting these common factors is a very important thing. How do we choose the number of factors? Well, that's where the likelihood ratio test comes into play. Also, we can look at these residuals based upon the correlation matrix to make a judgment of, okay, is this factor analysis model really getting at that correlation structure? These common factors, unfortunately, fortunately or unfortunately, have a non-unique interpretation. And that's where this whole idea of rotation comes into play. How do we do it? What's the intuitive understanding for that Varimax method? If you remember, it has to do with finding, essentially, the variances of the squared terms in the factor loadings matrix for each column. I could ask you, again, a short answer question is, well, explain to me why we are trying to maximize this V quantity for the Varimax method. And of course, we just saw some. You could do the plots of the loadings, but the whole thing with the factor analysis scores is not going to be on the test. And make sure you're very familiar with FactAnal. Okay, so the test is essentially 1 week from today. In the meantime, of course, you're welcome to post any questions that you may have on the discussion board. I'll be more than happy to answer it. Do you have any questions at this time about what's going to be on the tests? Okay, so that means everyone's going to get 100%, right? Well, if there's no questions, sorry, we're going to move on. And we're going to talk about cluster analysis then. So cluster analysis, just to take a look at where we are in the course. This is the last part of the summarizing data, let's say, section of the course. And we've kind of been, well, trying to achieve some of the goals of cluster analysis already whenever we looked at a plot of these common factor scores or the principal component scores, where we were trying to find groups of similar observations. Cluster analysis provides a formal way to do that. We will then go back to factor analysis or principal component analysis to try to justify our choices then for these groupings of these observations. So we'll actually do some plots of principal component scores once again, and then look at how these formal cluster analysis methods have tried to put certain observations together. Does it make sense? So the key with cluster analysis, or an element of cluster analysis, is that before we come into this, we don't have, let's say, any kind of grouping of the observations already. So like with the gobbles, we didn't have a grouping of the observations. That was the purpose of doing you could say that archaeological dig, is to try to come up with some kind of grouping eventually. And so with that, then, I want to talk about some terminology that you will see outside of this class. So computer scientists started getting into doing what statisticians have been doing for a long time. They started getting into what I am doing about 15 or so years ago. And I think they didn't necessarily realize that they were doing the stuff that we were already doing. And so they came up with a whole bunch of different terminology for some things. And in particular, they were doing a lot of the stuff that's in a multivariate analysis course. And they decided to introduce the term unsupervised learning and supervised learning. Have any of you heard of those terms before? Okay. So cluster analysis is what a computer scientist would say is a form of unsupervised learning. And I don't fully understand why they use the word supervise. The learning comes about from the concept of I'm learning from data. Okay. And what they mean by unsupervised is the fact that I don't have any kind of prior grouping of my observations to begin with, and I'm trying to essentially predict what those groupings should be. Now, supervised learning, and this is essentially the topic of section 3 of this course. So everything after cluster, mostly everything after cluster analysis. What that is I already have essentially a grouping of the observations, and I'm trying to predict that grouping. So you might remember my place kicking data set, where in football we have place kicks. They're either successes or failures. We can actually observe that. And given the, let's say, the distance of the place kick, given maybe some like the wind, given is there pressure on the place kicker to make the kick? Given those extra variables, we would like to be able to predict before the kick actually happened, is this going to be a success or is this going to be a failure? So what we can do is take a sample of actual place kicks that have been done, try to learn from them, and apply a supervised learning method that will predict, will this be a success or will this be a failure? That's what computer scientists will say is supervised learning. Statisticians, we've been doing this for over 100 years. And usually, or originally we were using, let's say, regression methods, but there's many other kinds of methods out there as well that we've developed. And now also computer scientists have developed some of their own methods in addition to replicate what we've already done. So unsupervised learning and supervised learning is within then a grand term that computer scientists have used that has really caught on, called machine learning. We just call it statistics. Okay. Now, there are a lot of cluster analysis methods out there. And in fact, I bet you could teach a whole course on cluster analysis. There's actually whole books on it. And so as you can imagine, we can't talk about everything with cluster analysis. We'll spend about, I think maybe about 2 weeks on it. And so we'll talk about the most commonly used methods out there. And if you find out that you really like this stuff, I encourage you to learn more about it then on your own. One place to start is on the CRAN website, Comprehensive Archive Network. There's a task view set up. Whenever there's like a large area in statistics, the organizers of R put together a web page called a task view, which tries to summarize all the packages out there that are meant for a particular statistical area. And so with cluster analysis, since it's so large, there is a particular, there is a particular task view out there. So to help set the scene here, let's go back to the goblet data. And this is a plot that we actually just kind of saw a little bit earlier today, where we had these informal groupings of the observations. Okay? And as I kind of alluded to, is that cluster analysis will help us formalize this a lot more. And so to see how cluster analysis works, let me make sure I'm not getting ahead of myself here. Hold on. Yeah, okay, good. So to help see how cluster analysis works, I have this program called twovariable.r. It's meant to be a very simple example where I have two variables in a data set and I have a total of 14 different observations. So we can see with these observations plotted that looks like some of them are similar to one another. Some of them maybe could be, let's say, grouped together. A natural grouping would be, let's say, this and this, or maybe I could do this, this, and so on. So each of these groupings in this area called cluster analysis are called clusters. Okay. So we need to decide, okay, well, should I use this grouping? Should I use a different grouping? Or why don't I, let's say, group these observations together? And it often comes down to is a measure of distance. But and it's easy to see this in a two-dimensional sense, but you can also think of distance in a three-dimensional, four-dimensional, five-dimensional, or as many dimensions as you want. You can think of distance that way. It's just it's going to be harder for us to see. So in cluster analysis, these measures of distances are actually referred to as measures of similarity or measures of dissimilarity. So observations that have a small distance are similar to one another. Observations that have a large distance are dissimilar to one another. The easiest way that we could actually measure distance is to use what's called a Euclidean distance. You maybe have seen this in another class before. And so let's say I have two observations. And just to be general, we call them observations R and observations S. They are p by 1 in dimension in terms of the vectors of the actual numerical values. So I have p variables still. And so to measure the actual Euclidean distance between two observations, I simply take the vector of the observations, I subtract them, transpose it, and then also do the same thing on the right side where I don't do the transpose. And then I take the square root of it. We've done something, well, so that's the distance between these two observations. People often refer to this as a ruler distance. So if I actually went to one of these plots here and actually measured it, and it was in the same scale as what you see in the x and y axis, that's essentially what I'm doing, taking a ruler to it. We could also look at the standardized Euclidean distance as well, where now we replace the x's with the z's. Why may this be a better measure of similarity or distance than using just a regular old Euclidean distance? What do you think? The scale. Or how about we think of it in terms of the variability of the observations? Some variables will have more variance than others, and we don't necessarily want that to factor in, what we say is similar. And so that's why we typically work with standardized variables in this particular case. Now, how can we actually, in R, calculate these distances? Well, you could obviously program that in yourself. But there's a nice function in R called dist that for, let's say, a data set that has capital N different observations, it will find all pairwise distances between observations for you. So now let's talk about clustering methods. As you can imagine, since I said you could teach a whole course on it, there's whole books on it, there are many, many different clustering methods. People generally think of these clustering methods as fitting into 3 different categories. The first category is called hierarchical. And the reason why it's called that is that this algorithm that's applied to find which observations are similar to one another and put them into clusters or groups does it in a hierarchical manner. Meaning, for example, and we'll eventually actually get into this. Suppose I find, we'll just do a Euclidean distance here since I've just, I only have x1 and x2 here. I don't have z1 and z2. Suppose I look throughout this plot and I try to find the 2 observations that are the most similar to one another. In other words, the closest to one another. What would I choose? Well, just by eyeballing it, you could say probably 13 and 14. So the way that a hierarchical clustering method will start is say, okay, let's join 13 and 14 together. Then it will say, okay, which next set of observations, or also groups, since I have now formed a group of 13 and 14, which is the next closest? So we can see, well, these kind of look close to one another. Maybe these look kind of close to one another. But how can I compare 13 and 14, this, let's say, cluster, to 11? Well, you'll see a variety of different ways. Maybe I should somehow, let's say, take a middle point here and measure the distance from this red dot to 11 to find the distance. Let's just say that that happens to be the smallest distance that we see overall. So now I'm going to form a new cluster. And so we keep on doing this process over and over and over again. And in fact, this will only end when everything is in one cluster. And so then it comes down to, okay, well, I don't want this all to be in one cluster. Where do I stop making these hierarchical groupings together? And that's going to be a big thing that we're going to be interested in. Now, alternatively, another way to think about clustering is, how about you start off with everything in one cluster, and now you say, okay, where's the largest distance here? Let's split stuff off. And so maybe I split stuff off into that. So those are two different ways to do a hierarchical clustering method, and they have specific names. The first one that I described, where we start off with all the observations essentially separate, and then we start joining them, is called agglomerative. Agglomerative is a word to mean grouping, coming together. And that's what I was describing to you at the very beginning. Now, if instead I decide to start off with everything in one, let's say, big cluster, and then start dividing things up, that's called divisive. We will focus on the agglomerative. That's applied much more. So, in terms of the three different ways to do cluster analysis, there's hierarchical. The second way is now non-hierarchical. As you might imagine, there's other names like partitional. And this is how this works. Suppose you come up with an initial guess somehow, just off the top of your head, and you say, I think there's going to be 5 clusters. And so what non-hierarchical will do is do an iterative method that tries to put all the observations into 5 clusters. You'll see what the iterative method what it is as we go along. But then you might be thinking, okay, well, what if I started with 3 clusters instead? What would happen? So you can apply this iterative method. And then you might be thinking, okay, well, maybe I'm not as sure in terms of how many clusters I should have. How can I choose between using 3, 5, 4, 10 clusters? And so there are methods out there that help you make that decision. This is non-hierarchical, and we will focus on one particular non-hierarchical method later in these notes. And lastly, there is what's called model-based clustering, where you assume some kind of statistical model for your data, and that model then helps you figure out what the clusters are. I will not, though, talk about that particular method in class. While it is used, it's not used as much as the other 2 classifications. Okay. Let me see here. Since we're not going to come back to this for a week and a half, I think this might be a good place to stop. And then once we get back to having a normal class, we will start talking about one specific agglomerative agglomerative clustering method called nearest neighbor, the nearest neighbor method. So otherwise, I'm going to have to probably review it all anyway in a week and a half. So we're going to get out 10 minutes early today. So, any last questions? Okay, and that's all for today.